Hello, everyone. My name is Andrej Kržič, and I work as a research assistant at the Fraunhofer Institute for Applied Optics and Precision Engineering, or shortly Fraunhofer IOF, located in Jena, Germany. Today, I would like to present you the work that we have done towards practical metropolitan free space quantum key distribution networks. Now, let's start with the basics. Quantum key distribution, in a nutshell, is about generation and distribution of a secret key of which security is based on quantum mechanics. So without the loss of generality, let's imagine two communicating parties, it could be also more, who try to establish a common cryptographic key. So they do this by the means of transmitting quantum states and measuring them with a specific quantum measurement according to a certain protocol that we are using. And at the end, they would like to generate a string of bits that would be, first of all, identical. And second of all, it would be secure, meaning that no potential eavesdropper would even hypothetically be able to compromise the security of such a key. It is without a doubt the most technologically mature form of quantum communication. As you might know, it has been around already for about 4 decades now, and it has come a long way since there. So there have been many experiments successfully performed. Most notably, recently, quantum key distribution has been performed even from space. Therefore, a lot of fundamental research has moved on beyond quantum key distribution. However, in the more applied domain, what we are currently focusing on is to try to improve the quantum key distribution from the more practical point of view. So if we identify as the ultimate goal large-scale QKD networks, then the idea is that we would like to now increase the key rates, we would like to improve the scalability of the QKD networks, and, for example, also to make them available around the clock. When it comes to large-scale QKD networks, we can divide the whole idea into 2 domains. Over very long distances, say here we are talking about over 500 kilometers and more, free space links via satellites seem to be the only option. And this is simply due to the exponentially growing loss over the optical fibers. On the other hand, over metropolitan areas, or shorter metropolitan areas, typically optical fiber links are still preferred. Now, that brings us to a problem. Suitable fiber infrastructure might actually not be always available. So imagine, for example, that there's a relatively spontaneous summit or event or a conference of some sort, and the fiber infrastructure is not in place. And the first alternative that pops into our mind is to try to do the QKD via free space. Now, while this is, of course, a feasible option, it is still lagging behind, quite considerably behind the well-established fiber-based approaches. One might say that this is simply because free space sector has not gained as much, not nearly as much as the fiber-based sector has from the classical communications. So I will be focusing here on the approach that is based on quantum entanglement. Imagine that we have an entangled photon source, which we will be calling here an entanglement server, that sits on the top of a high-rise building and streams entangled photons to end users via free space links. Each of the end users needs to be equipped with a quantum receiver system, and this system incorporates quantum measurement, post-processing that consists of privacy amplification, error correction, and all these things. And finally, it outputs the key. Now, what you can also see is that such an approach is not strictly limited to free space. It could be very easily interfaced also with optical fibers. So, for example, the host building of the entanglement server, within that building, people could simply connect to the entanglement server via optical fibers. Or if we would like to connect such a local area network to a broader quantum network, we could also use optical fibers for that. Now, I would like to make the case here, particularly for entanglement-based approach, for a couple of reasons. First of all, entanglement allows us to create a fully connected mesh at the quantum communication level. So on the physical level, this topology looks like a star-shaped topology, but if we perform multiplexing, for example, in the wavelength degree of freedom, as it has been shown to work really well in fiber networks already, we could create cryptographic keys pairwise between any two pair of users. Furthermore, entanglement server does not need to be trusted. It can therefore act as an untrusted node, which in this particular case of free space configuration can very conveniently act as a relay, meaning that there doesn't need to be a direct line of sight between the two users that want to communicate. Now, this is very practical. And there's another advantage. Entanglement server is all passive, while all the processing is actually done at the end users. That allows us to standardize the entanglement server, and it allows the users to use application-specific software on their end. This also allows then the users to upgrade their server, maybe change to a different protocol, and so on, because the entanglement server does not care what the users do with those entanglement photons. I would also just like to spend a minute discussing the scalability. So if we start with a simple star-shaped network, as was just presented, where we have a central untrusted entanglement server and several end users with their own quantum receivers, what we could do in midterm is connect several such smaller networks into a larger network, which would be connected through one trusted node in between. Now, this would actually have as a consequence the fact that we lost the untrusted node. So now we have to start trusting the central node. But what's good about this is that as entanglement swapping becomes practically more available, we could simply exchange this trusted node by an entanglement swapping node, and this would then bring back the advantage of being untrusted, while we could still keep the same physical layout. So when we do quantum communication over free space links, there's one very particular issue that in fibers is simply not encountered, and this is called sunlight. What happens is that as we establish the link, we have our very weak quantum signal traveling usually along horizontal direction towards our receiver telescope, and sunlight gets scattered in the atmosphere. And this scattered sunlight is then getting captured by our receiver telescope. And if we do a simple back of the envelope calculation about how much sunlight would we expect to be scattered into our telescope, we arrive at very grave numbers. Namely, the typical daylight noise would be expected to be in the range of 10 to the power of 10 photons per second per nanometer of the spectral bandwidth. Now, if we compare this to the typical signal levels that are expected, for example, such that we had here in this work, they would be in the level of 10 to the power of 5 photons per second. So we see there's 5 orders of magnitudes difference, and this can have very, very deteriorating consequences on our quantum key distribution. What this means is that we need very strong filtering of noise in all possible degrees of freedom. Temporal filtering is in entanglement-based systems very conveniently implemented via the coincidence-based detection. This means that we are only listening, or we are only sensitive to events that occur simultaneously at Alice and Bob, and this essentially imposes a temporal filtering of our signal. Now, spectral filtering is even easier than that. What we usually do is just employ some off-the-shelf interference filters. There's also more sophisticated methods, but what is really difficult is to perform spatial filtering. Spatial filtering usually means that we would like to reduce the receiver field of view. So what the receiver field of view is simply an acceptance cone of the angles that the telescope will accept. So how we can change this is, if you imagine every telescope has some primary optics, and this primary optics has a certain focal distance. And if we put what we call a field stop into the focal plane, the size of this field stop basically determines the size of the acceptance cone. So the smaller the field stop, the smaller the acceptance cone. And this is then a big advantage, because we know that the signal photons are mostly originating along the optical axis, meaning that they are nicely collimated, while the scattered light is distributed over a larger range of angles. So if we reduce this field of view down to the size that only permits the signal to go through, while blocks the majority of the noise, then we could gain a certain advantage. But to complicate things even more, there's another effect that the turbulence has on our incoming signal. Namely, it aberrates its wavefronts. And an aberrated beam will then, as a consequence, not be focused as nicely as a non-aberrated beam. So you see here with a solid line, we have a very, very narrow focal distribution of light here. And then we could use a very small aperture, a very small field stop to get the signal through. But if there's atmospheric turbulence present, then this spot is going to spread, and it's going to force us to use much larger field stop in order to have our signal pass. So let's conclude this introduction just by a brief dive into the state of the art. And here we limit ourselves only to the demonstrations that were done in free space over metropolitan distances and used entangled photons as the resource. What you can see is that quite a while ago already, a successful demonstration over about 10 kilometers had been performed, and the key rates with about 10 bits per second were achieved. If we go to the other end of the spectrum, quite recently, very high bit rates of about 1.7 kilobits per second were achieved, however, over much shorter distances of 200 meters. Now, one thing a few of you might be surprised at is that there's only 7 of these demonstrations. So in the past 20 years, only 7 demonstrations of metropolitan scale free space QPD. Just note here that we are excluding, of course, the successful satellite implementations and implementations that were done over longer than kilometers of length, because they were done with a specific goal of satellite communication in mind, whereas we would here really like to focus on metropolitan implementations. So, as I said, there have been only 7 successful implementations so far over metropolitan distances, and only one of those has successfully tackled the issues of the daylight noise. So you see they achieved about 300 bits per second over a 350 meter link in daytime. Okay, so how did we tackle the issue at our institute? We first developed a special free space terminals that could be used for various forms of quantum communication. So for different experiments. This, however, what I will be showing today is just the first of a series of experiments that we are planning. So first of all, we wanted our telescope system to be versatile, to support several wavelength channels, to be breadboard based, which allows us to improvise and prototype on the fly as we implement the experiment. And also we have a symmetric design. So there are 2 such systems as you see here on the picture, one acting as a transmitter, the other one as a receiver, but we could always just switch and use it in vice versa configuration. But what is even more important is we wanted them to be efficient. So we designed very large primary aperture of about 200 millimeters in diameter. And what's even more crucial is that we didn't have any central obstruction. So we had an off-axis mirror design, and the advantage of such an off-axis mirror design is that we can indeed avoid having this central obstruction that usually such large mirror-based telescopes are forced to have. So that allowed for very high throughput of the telescope. And furthermore, we implemented adaptive beam stabilization to fight the atmospheric turbulence problems that I have just presented a couple of slides ago. Last but not least, maybe it's not so strictly relevant for the experiment I'm going to show, but it does make a statement about practicality of free space systems as compared to fiber-based. Our system can be deployed in less than a day. The free space link that we used for our experiments is our local Fraunhofer link in Jena, which was implemented between a laboratory at our institute and a temporary container on the rooftop of a public service building. The distance between the two sites is 1.7 kilometers, and the orientation is northwest to southeast, with southeast being here on the rooftop, and also here on the rooftop we positioned our receiver system. We measured our link efficiency to be about 50%, which is quite a decent efficiency for such distances. Now, let's talk about the QKD architecture that was employed for these experiments. So we implemented the BBM92 protocol, which is, as most of you know, just a variant of the famous BB84 protocol that is based on quantum entanglement. And we start with an entanglement server, which produces Bell states of such form, and they are entangled in polarization. So H and V here represent horizontal and vertical polarization, and A and B stand for Alice and Bob channel. We were using the wavelength of 810 nanometers, and such source had two fiber outputs. First fiber led photons directly to Alice, where Alice used the polarization analysis module to measure their polarization, and finally detection and post-processing system, which looked like that. It consisted of 4 SPADs, or single photon avalanche detectors, which were connected to a time tagger. Time tagger was run by a rubidium clock, and all the measurements were finally fed into our post-processing unit, which, as I already mentioned, implemented the synchronization, the error correction, primacy amplification, and finally distilled the secure key, which was used for encryption. Now, the other photon of the pair traveled through the free space terminals over this 1.7 kilometer link, while getting received by Bob on the other side. And since now the photons were already in free space, we actually mounted the polarization analysis module of Bob directly onto the free space terminal. This is where the breadboard design really came handy. And because we were here dealing with the environmental issues originating from this free space link, we also had to implement spectral filters and spatial filters. Finally, similarly as at Alice, photons were measured in horizontal, vertical, diagonal, or anti-diagonal setting and post-processed. What we need to successfully perform such a quantum communication protocol, we need also a classical communication channel, where, just as a reminder again, the temporal filtering took place via the coincidence-based detection. And this brings us to the results. What we did is we used the present system under various link conditions during the nighttime, during a cloudy day, and then also during a cloudless sunny day. And let's start first with the simplest of the experiments, which was performed during the night. So you see, during the night, we achieved a very stable secure key rate of about 6 bits per second, and the corresponding error rate was below 2%. This somehow defines the benchmark scenario of, let's say, the best of what our system is capable of doing over such a link. Next, I would like to show you the results we achieved during the day, but it was a very cloudy day. As you can see on this picture, it wasn't very bright on that day, and consequently, what you can see is that we achieved almost our benchmark performance throughout the whole day. You see that even when the sunlight peeked through the clouds slightly at this point, it didn't disturb the overall quantum key distribution. Just as a note, the background here basically represents the solar radiation that was measured at a weather station independently of our experiments. But the most interesting set of experiments was actually performed the day after, when we had, at least in the morning, we had completely cloud-free conditions. So we started early, around 8 in the morning, and you see that the secure key rates started at about 5 kilobits per second and started dropping while the sun started raising above the container towards the zenith. And you see that at the point when it was the brightest, we achieved still more than about 2 kilobits per second of secure keys. But then something interesting started happening. Some clouds formed on the sky, which created variable sunlight, right? So what you can see is that then the secure key rate started jumping up and down and up and down according to the exposure of the link to the sun, and also you can see the same happen to the error rate just in the other way. So when it became dark, the error went down. When it became bright, the error went up and down and up, so on. Note, however, that this last drop here had nothing to do with daylight. We later identified that this was simply due to a sudden drop of performance of our entangled photon source. So in conclusion, we were able to achieve up to 6 kilobits secure key rates with about 2 kilobits per second in daytime. And as you can see, the level of noise suppression was just enough. If we had slightly less noise suppression here, we probably wouldn't be able to achieve kilobit secure key rates. And let's just have a quick look also into what kind of signal and noise levels were we talking about here. So this is from this variable daylight experiment, when the brightness changed due to the partly cloudy conditions. And what you can see here with a solid green line is the noise signals measured at the receiver, at Bob. And what you see with the dashed green line is the corresponding signal photons received at Bob. And what you can see is that at the worst times, the signal was about 4 times lower than the noise, and the noise actually even surpassed about 400,000 of photons per second. Quite interestingly, or not, the solar radiation measured completely independently with a pyranometer at a weather station shows a very nice correspondence to the noise levels. You see it here with this orange solid line, and you see it very well follows the dynamics of the noise photons. If somebody is interested, here are the filtering parameters that we used for this experiment. Coincidence window was at 1 nanosecond. We used a 3 nanometer bandwidth spectral filter. And maybe most interestingly here, we reduced the spatial filter field of view down to 31 microradians, which is about 100 times less than the telescope intrinsic field of view. However, this is a linear field of view, so if we want to know how much the noise level actually decreased, the noise rate is depending quadratically on the linear field of view. This means that we had about a 4 orders of magnitude reduction of the noise rate simply due to the spatial filter employed. So in conclusion, we have shown that free space links are a viable alternative for metropolitan scale QKD networks. We wanted to show that entanglement-based solutions are particularly attractive where the entanglement source acts as a passive server. Moreover, we demonstrated kilobits per second secure key rates over a 1.7 kilometer link in night and day. This shows a clear potential for 24/7 availability of secure key services. And it's about an order of magnitude improvement with respect to state of the art. And finally, we made some back of the envelope estimations of what would we expect with our system over longer, maybe 10-kilometer links. And we arrived at the conclusion that also kilobits per second rates should be possible, at least in nighttime. So that leads me to my final slide, where I would just like to acknowledge my team, in particular, Uday, Sakshi, Christopher, Sebastian, Matthias, and our group leader, Fabian Steinlechner. I would also like to encourage everyone that has any questions to address them to my email that you can see here. And yeah, thank you very much for your attention, and hope to receive some questions. Bye-bye.